All right. So let's move on and discuss some identities involving partial derivatives. So some identities. So we can think of the function u, which is a function of x and y, as a surface. As a surface in a three-dimensional space, whose axes are u, x, and y, right? So for example, if I go here, we can think of this, this red surface, this red function is a surface in a three-dimensional space with x, y, and u, right? So, just as from here, we wrote d of u as du by dx of y, d of x, du by dy, x dy. What we can do is that we can invert this function. It may be that to invert this function, we have to restrict the domain because of issues of double valuedness and stuff like that, but we're going to gloss over those subtleties here. We can invert this function and express x as a function of u and y, right? So what we're doing is that we can play with what is the dependent variable, what is the independent variable. So if I do this, then I can now, again, use the same analysis. So I can consider a change in dx, along the same path, and it'll be, say, dx by du of y of du plus dx of dy u dy. Sorry. Okay. So now what we can do is that we can say, okay, what if we take this equation, let's call this equation 2, and insert it in equation 1. So we eliminate dx using this guy. Then what do we get? We get d of u on the left-hand side. On the right-hand side, after a little bit of rearranging, what we get is that we get a term which is du dx of y dx du y times du. So this is basically, this term and this term multiplying. And then we get another term, which is du dx of y dx dy u plus du dy of x d of y. And this is, this guy multiplying this guy and this guy. Okay? So of course, the left-hand side and the right-hand side should agree. And therefore, this should be 1 and this should be 0. So consistency demands that we have d of u by d of x at a constant y is nothing but 1 divided by d of x d of u at constant y. So this is, equation number A. The other thing is that this should be 0. So that means that we should get another identity, which is d of u, d of x at y, and d of x, d of y at u equal to minus d of u, d of y of x. But what we can do is that we can use this equation on the right-hand side here and convert that into something nice looking. And so this combining, we get d of u, d of x, y, d of x, d of y, u, d of y, d of u, x, which is the inverse of this, is equal to -1. So this is equation C. Okay? So these are useful identities, which just comes from some almost trivial manipulation. Okay, any questions?
Sir, can these double valuedness be safely ignored in the context of thermodynamics? যে আমরা যে x equals to x is a function of u or y লিখলাম?
Uh, Actually, no, I don't think so.
Oh,
There are things like phase transitions and things like that where you have to be aware of these things. And a lot of nice physics comes out from these subtleties, right?
mhm.
So this is just to kind of like when you're given a function and you try to invert the function and you find that there's more than one branch of the function, then of course you have to be specific about which branch you are looking at, right? So this is in complex analysis. This is really what gives rise to branch cuts and Riemann surfaces and stuff like that, right? So multi-valuedness is a part and parcel of life, and it's a very useful part and parcel of life. So we have to be aware of that. So I don't. So my answer would be in most cases yes, you can ignore them, but especially for this class. But maybe in the future when you're actually doing a more advanced class or you're doing some research project, one needs to be careful. Okay.
Yeah, okay, sir.
All right. So any more questions?
So there was another identity. I mean, the mixed equality of the mixed partial. Is there any geometric interpretation for it? I've been searching for years if there was any.
For this guy?
No, the equality of mixed partials. The order doesn't matter in which variables you differentiate. Like this,
Right. Yeah.
yeah, a geometric interpretation for it, at least for the two-dimensional case. I never found it actually. Tried to visualize it, but it doesn't work.
Right. So yeah, that's a very interesting question, and hopefully what I'm going to tell you next is going to shed some light on it. Okay.